Okay, welcome to Lecture 6 for Discrete Mathematics. This is called Rules of Inference, Part 1. So today we're going to talk about arguments and inferences in propositional logic. Okay, so what is an argument? It's simply a sequence of propositions. So we've dealt with propositions, we know what they look like, how we can define them and assign them to a letter in propositional logic. Now we can put them together. So all but the final proposition in an argument are called premises. The final proposition is the conclusion. So for example, premise number 1, if you have a password, you can log on. Premise number 2, you have a password. The conclusion then is you can log on. We're going to see exactly which argument type this is, which rule of inference this uses, but this is a basic example of an argument. And we say an argument is valid if whenever all the premises are true, the conclusion must be true. Okay? So validity isn't assuming that the premises are true. It's just saying that if they were true, then the conclusion would have to follow from that. Okay, that's all a valid argument is saying. Now let's look at the actual rules of inferences. So these rules are tools used for building valid arguments in logic. They help us move from premises to conclusions in a systematic way. And this is a way that's going to be, at least in propositional logic, without concern for the actual content of the statement. So once we've translated this into propositional logic with symbols, these rules of inferences are going to help us connect different propositions. Okay, so while truth tables are possible, they become impractical with many variables. Rules of inference, on the other hand, give us shortcuts for reasoning. So let us look at the first example, our first rule of inference. This is called Modus Ponens. Okay, so this is a Latin name for what's going on here. The idea is that our first premise is a conditional statement, if P then Q. Our second premise is the antecedent of this conditional. It's P. Okay, so it's saying, well, if we have if P then Q, and you have P, you know that P is true, well, then the consequent must follow. We have to be able to conclude the consequent, Q. We can take it out of that conditional statement. Okay, so let's suppose that P means there is fire. Q means there is oxygen. Okay, so if we're using these two definitions to translate from symbolic to English, we'd say if there is fire, then there is oxygen for our first premise. Second premise is saying, well, there is fire. So the conclusion is saying, well, then there must be oxygen. Okay? That's it. That's modus ponens. So it's allowing you to take that first part of your conditional and use it to conclude the second part. Then we've got what's called Modus Tollens. So if our first premise is again the conditional, if P then Q, and our second premise is the negation of Q, this is going to allow us to conclude the negation of P. And really what's going on here is it's kind of working off the contrapositive. Okay, so if you remember the contrapositive, it takes this form, right? So if we had if P then Q, the contrapositive would be if not Q, then not P. Okay, and this is implied by the original conditional statement. So in the cases where this is true, its contrapositive is also true. And this is really just the antecedent of the contrapositive. And this is the consequent of the contrapositive, right? So it's almost like you're just doing modus ponens on the contrapositive of whatever conditional you're given. Okay? So again, let P mean there is fire, let Q mean there is oxygen. So if there is fire, then there is oxygen. Well, if there's no oxygen, then we can conclude that there's no fire. Remember, this is the necessary case, or the necessary factor. This is the sufficient factor. So if we take away what is necessary for fire to exist, which is oxygen, well, then we can conclude there's no fire. Okay, so that's Modus Tollens. Our third rule of inference is called the Hypothetical Syllogism. So this is built off our first premise, if P then Q. Our second premise is another conditional, if Q then R. And then we can go ahead and we can just conclude, well, if P, then R. We can just kind of cut around that middle step. You know, if this implies this and this implies this, well, then you can automatically conclude that P implies R. Okay, so P is defined, there is fire. Q is defined as there is oxygen. Let's define R as, well, rusting can occur. So if there is fire, then there is oxygen. If there's oxygen, then rusting can occur on whatever metals happen to be in this environment. So you can kind of conclude that if there is fire, rusting can occur on those metals. Okay, so we can just cut around that oxygen part completely and go from P to R. That's the hypothetical syllogism. This is going to allow us to connect any two conditionals where the consequent of the first conditional is the antecedent of the next one. Number 4, we've got the disjunctive syllogism. P or Q is our first premise. Negation P is our second premise. And this allows us to conclude Q. Okay, well, we said, well, one or the other has to be true, and it's not the first one. Well, then it must be the second one. So let's see how this looks. Let P mean it is raining. Let Q mean the ground is dry. So that first statement is going to translate into it is raining or the ground is dry. Well, it's not raining. And that means the ground must be dry. Okay? So this is just eliminating one of the disjuncts in your or statement. That allows us to conclude the other one. Okay, rule number 5 is called addition. And for any proposition P, we're allowed to add a second proposition Q using the disjunction. Okay? Because in order for a disjunction to be true, only one element needs to be true. So if we know for a fact that P is true, well, we can always just add that second element. Whether or not it's actually true, we can still make that statement. And this can be really useful in arguments or proofs where we need to construct this in order to, I don't know, say get the antecedent in a conditional or something like that, right? So this rule allows us to do this. Let P mean I will study discrete math. Let Q mean I will visit Las Vegas. So if we know for a fact that I will study discrete math is true, we can just tack on that, or I'll visit Las Vegas part to the end of it. Okay? Now we've got rule number 6. This is called simplification. And it's kind of going the other way. Now if we have a conjunction, remember, we know that a conjunction is only true when both atomics, both elements in it are true as well. So simplification allows us to take any conjunction and conclude one of those elements. Okay, so if we know P and Q is true, well, we can conclude either P or even Q if we wanted to. Okay, so this would also work the other way. We could just use this to conclude Q, the other conjunct. Okay, so let P mean I will study discrete math. Let Q mean I will study calculus. If we know you're going to do both of these, well, then we know that either one is true. We'll also study discrete math. Okay? And separately, in a separate instance, we could have also just concluded I will study calculus. Okay? That would have also been valid by simplification. Okay, and then this is about going back up and building that conjunction. Okay, so rule number 7 is a conjunction rule. If we have both these elements, P and Q, we can put them together. Okay, so the same ones, I will study discrete math, I will study calculus. We can go ahead and we can construct that sentence. So this is just going the opposite way as a simplification. I will study discrete math and calculus. Okay, so notice for a disjunction up here, where did it go? Addition. Here it is. For addition, you only need one element to be true, and you can add on that Q element, whether or not you know it's true. But for a conjunction, you need to have established that both of those elements are true before you can put them together with a conjunction. Okay. And our last rule is called resolution. So we start off with the statement P or Q. We've got another statement, negation P or R. And this allows us to conclude Q or R. Okay? So let's suppose P means I will study discrete math, Q means I will go to the beach, R means I will go to the gym. So that first statement is going to translate as I will study discrete math or I will go to the beach. The second one says I will not study discrete math or I will go to the gym. And the last one, I will go to the beach or I will go to the gym. All right, so those are our 8 basic rules of inference. Now let's talk about building valid arguments. Well, a valid argument is really just a chain of statements, and it's going to take this sort of form. So you've got your premises, S1, S2, all the way down to Sn, however many premises you have. And then you're going to be able to draw a conclusion, some conclusion C. Okay? In other words, a conclusion C follows from a sequence of premises S. And oftentimes, to get from one step to another in your premises, we're going to use rules of inference. Okay? So let's see how this looks in an example. So from the single proposition P and if P then Q, show that Q is a conclusion. So to start off, let's list out our premise. Well, in this case, we only have just the one given premise. Okay. Now, from this given premise, we can break this conjunction apart, because if it's a conjunction, we know that each individual element of that conjunction has to be true. So we're allowed to conclude P by using simplification on 1, and we're allowed to conclude the conditional in step 3, also by using simplification on 1. So we can break that apart and conclude each element individually. Now, we have a conditional, and we have the antecedent of that conditional. So by Modus Ponens, our first rule of inference, we're allowed to conclude the consequent. Okay, so we said we were using Modus Ponens on 2 and 3. So we can use this antecedent to just break this conditional apart and get that consequent out of there. Okay, so this is a basic example of a valid argument. Let's look at another example. Now we've got the following propositions. Okay, and we are trying to conclude this. So our propositions: it is not sunny this afternoon, and it is colder than yesterday. We will go swimming only if it is sunny. Number 3, if we do not go swimming, then we will take a canoe trip. Number 4, if we take a canoe trip, then we will be home by sunset. And we want to use all of these propositions, all of these premises, to construct a valid argument for the conclusion we will be home by sunset. Okay, let's see how this works. So let's first of all define all of our propositional variables. Okay, so we're going to separate this not out of here. So we need this factor over here. Do this in green. So we need the fact that it's sunny this afternoon. Let P equal it's sunny this afternoon. It is colder than yesterday. That's going to become Q. We will go swimming. That'll be R. We've got an only if. This is a connective, right? This is going to be using our conditional. If it is, so we'll go swimming only if it is sunny. We've got that already for P. If, then, that's in our conditional. So the antecedent here is we do not go swimming. So it's going to be a negation of R. Then we will take a canoe trip. So we need a new one for canoe trip. That's S. And finally, we've got last conditional. If we go take a canoe trip, we will be home by sunset. So we're going to make T, we will be home by sunset. All right, so let's go ahead and construct our symbolic statements. Translate each premise and the conclusion into propositional logic. So it is not sunny this afternoon is going to become negation P. And is going to give us the conjunction. It is colder than yesterday. That's just Q. We will go swimming only if it is sunny. So we will go swimming is the antecedent. Sunny is the consequent. Okay, so when you have this kind of only if statement, we'll go swimming only if it is sunny. We're saying that this is the necessary case, right, or the necessary condition in order for us to go swimming. Okay, so in a conditional, the necessary comes after the conditional sign. And the sufficient case comes before. So sufficient is your antecedent, your consequent is necessary. So we just translated in that order for only if. Okay. If we do not go swimming, then we will take a canoe trip. So if we do not go swimming, it's going to be negation R. Then we will take a canoe trip. That's just S. Finally, if we take a canoe trip, then we will be home by sunset. Canoe trip, again, S. Home by sunset, that's T. And same deal for this, right? So our conclusion, we just want T by itself. We will be home by sunset. So let's see how this is going to look. Now we want to construct the valid argument. Let's first of all take our 4 premises from here. And we're going to start just by listing those. These are all of our given conditions. Now let's see what we can break apart. So let's do a simplification on 1, right? Because we had a conjunction of not P and Q. So let's break that apart. That'll give us a not P. Now this is nice because if you remember, Modus Tollens works on the contrapositive. Okay, so if R then P implies, well, if not P, then not R. Okay, so we've got not P here. This is going to allow us, Modus Tollens is going to allow us to conclude not R. Okay, so Modus Tollens using 5 on the conditional and 2. And that gives us not R. Now that we've got not R, I see in premise number 3 over here, that's the antecedent. So we can just go ahead and we can use Modus Ponens on this, and we can conclude S. So Modus Ponens using 6 on 3. Now that we've got S, let's just go ahead and we'll just use Modus Ponens again. On line 4, we should be able to conclude T. And that's it. So Modus Ponens using 7, which is our S, on premise number 4, and that isolates our consequent. Okay, so this was a quick look at how rules of inference work in propositional logic, and how they're going to allow us to take our premises and isolate whichever statements or conclusions that we would like to do. All right. So this was Rules of Inference Part 1. Thank you for watching. If you liked this video, please hit the like button, subscribe so you don't miss the next one. Thank you.